We're finally ready to put together the power supply, which will mean ultimately soldering the components from the electrical e-bag into the power supply printed circuit board. Here's a schematic. I printed this out from the link from Cincy on their GitHub page. It's links in the course notes, and it's basically what we're putting together. This printed circuit board is created from this actual schematic. And so we're going to go through it. The purpose is to take power in, which will come not shown on this board, from the 12-volt AC plug that goes through a rocker switch to turn it on and off. So those will not be soldered onto this board, be attached separately. And wires from that will go into this ACN terminal. And then the output is going to go to a standard Eurorack style so-called IDC ribbon cable assembly, and this is the header or solderable connector for that. All Eurorack power supplies have either a 10 or 16 pin header. We're doing only the 10 pin version of this course. And as you can see, it's 2 rows of 5, and the convention is that each pin across from each other is connected the same one. So 10 and 9 are connected, 2 and 1 are connected, and in particular these ones on the outside hold the voltage. So up here, 9 and 10 have the plus 12 volts, and 1 and 2 have the minus 12 volts, and the ones in the middle are all connected to ground. And so that's the end goal, is to get over to this connector, and then I'll show you in a separate video how this connects to actual ribbon cable that distributes power to all the modules. So let's go through our parts and the ideas real quick. We see over here the opposite pointed diodes, which are of course from the voltage doubler, which I built and demonstrated already for you. We'll have to make sure those go in the proper polarity. There are 4 large 1000 microfarad capacitors. There are 200 microfarad capacitors for a bit of extra filtering on the pre-voltage regulator side. And so far we've got what really looks like our, on the capacitors there, it'll be these red ones, the 100 microfarads. We've got basically what looks like our voltage doubler. Now here we put the voltage regulators, right? Because the idea is we have this filtered supply that's given us, say, plus minus 17 or 18 volts DC out of the initial 12 volts AC. And now we use these regulators. They drop the voltage down and give us a very precise output. And one of them, which is the 7812 here, gives us plus 12 volts. And then the 7912, which goes down here, will give us minus 12 volts. And it's very important you do not swap these two. They look similar. Please check you have the 7812 on this side and the 7912 on this side to make sure you get them right. It's actually so important that it's noted which goes where, 7812 or 7912 on the PCB. Now the data sheet for these integrated circuits, which I've brought up here. So this is from Texas Instruments. It's the data sheet for the 7812, 7912 is similar, just opposite. Suggests that when you have transient voltages, and we're going to have transient voltages because ultimately we're going to switch them on, with a rocker switch, you put a large capacitor, which is going to be an electrolytic before. Clearly we have plenty of those on the input side. And on the output side, we also put capacitors. This helps prevent some of those large voltage transients from the switching from making it to the output. And then finally, it recommends for protection to put an input breakdown diode. So it's a diode pointing in this direction. So imagine we have plus 12 volts, that's creating a current running in here, or say plus 17 volts, a current running in here, and then plus 12 volts is creating a current running out this direction. fast fluctuations get shorted to ground through the capacitor. Any return voltage actually will bypass the integrated circuit, the 7812 or 7912, and go out the input. So that's the idea of this capacitor, which is called a series input breakdown diode. And this would be then some transient suppression on the output. So this actually idea comes from the data sheet. Let's look at those parts. So we do some filtering on the output as well, both on the positive and negative side. There's a microfarad capacitor, still electrolytic, so you have to worry about the polarity. Again, the long end or the plus side always goes to the higher voltage. Then there's just a couple small for very fast transients, 100 nanofarad ceramic capacitors, or multi-layer ceramics in this case. And then finally, just some extra diodes, which also help with currents, preventing currents from going sort of backwards through the circuit. So again, you'll notice from the position of these diodes that if there was a current running this way, it would get shorted to ground before it made it to the IC or the electrolytic capacitors. Let's put our little diodes in place here as well. And then all we're left is with really is the indicator. Indicator is going to be an LED. This box indicates a ground connection that isn't made on the actual circuit diagram. So imagine this ground here goes to the ground on the other side of the LED. We're going to attach the LED last and on the wrong side of the circuit board so we can see it from the front. More details on how that works in a minute. And of course, because it's an LED, it needs a current limiting resistor. Here we use the suggested 2K. The only thing left is there will also be a couple of heat sinks. Heat sinks are used to dissipate heat from these integrated circuits. We'll attach those at the very end.